Before I start, I'd like to thank Luca and Loredana for giving me the opportunity to speak here, and I'd also like to thank Katie for agreeing to switch with me. I am not Katie, I'm Betsy. Yes. So what I'll be talking about is extremely related to the work that Philip just talked about, and I'll be focusing more on something that he briefly stated, which is on a bound for a type of operator that's called a generalized Radon transform. And so in general, this is a generalized Radon transform is an operator that's of this form, Tf of x equals the integral on Sx of f of y d sigma x of y. And here, let me tell you what these things are. So first of all, the point x is an element of Rd. This guy, S sub x, is going to be a manifold, which often is allowed to vary in x. This is going to be a k-dimensional. So k will be fixed, and it's a submanifold of R to the n, and that's where y is going to lie. And d sigma x is a measure on S sub x. And there's also the condition, I'm not going to really explain this, but S sub x, d sigma x are assumed to be smooth in x, whatever that means. And so one program in the harmonic analysis literature is to determine for exactly which PQ operators of this form satisfy a bound norm of TF in LP of RD less than or equal to a constant times the norm of F in LQ of R to the n for some constant c less than infinity. And so this is a major program, and I won't even be able to come close to telling you about everything in this program in 15 minutes. And so what I'm going to do is I'm going to focus on a very special case, which is when d equals n, and the constant k is equal to 1. So this means that these manifolds S sub x are going to be curves. And even more specifically, I'll focus on the case when the S sub x are all translates of some fixed curve. So now I'll specify things even more. So first of all, which P and Q are we interested in? Well, usually the case is when P is smaller than Q. And so we're going from LP into LQ, and so this exponent is getting bigger. And this is called an LP improving estimate. So one thing about why we would consider this case is that if sigma x of S sub x is finite, so if this is less than or equal to some constant, less than infinity, then the LP to LP bounds are trivial. And there's also, so in the case, and so we aren't going to really think about those, there's also the case when P is greater than Q, and more or less this either in the cases of interest, this either turns out to be trivial or false, and so we don't think about that often. So a necessary condition for this is that the manifolds Sx exhibit some sort of curvature. And so a non-example would be that if S sub x were equal to x plus some line segment. And that would turn out not to have any LP improving properties. Something else, so you want your curve to actually be genuinely d-dimensional, and you want some higher order notion of curvature. And the model case for this is the curve S sub x equals x minus t squared yada through t to the d. And you can restrict t to the interval from -1 to 1. And so this means that the operator is Tf of x equals the integral from -1 to 1 of f of x minus t squared yada through t to the d. This is sometimes called the moment curve. So a brief history, some work began in 1973, and there's been significant progress on the problem of LP to LQ bounds by Littman, Oberlin, Christ, and some others. And the issue has finally been completely resolved, and that's what I'm going to talk about. So next I'll talk a little bit about the earlier work. So in 1973, Littman, and then in 97 and 99, Oberlin used Fourier transform techniques and they establish optimal bounds in dimensions 4 and lower. So in 98, Chris used a completely different technique, which is now important in the harmonic analysis literature, and I'm going to go into a little bit more depth for that, because this is more along the lines of what the arguments that I used. So what we're going to do is forget about trying to prove LP to LQ, which are called strong type estimates, and try to prove instead LP, 1 to LQ, infinity, or restricted weak type estimates. Of course, this isn't the major new idea. Trying to prove a simpler problem is common in all of math, but now I'll talk a little more about the proof of the restricted weak type estimates. So for an LP1, LQ infinity estimate, what you want is for the inner product of t applied to a characteristic function and then tested against a characteristic function to be less than or equal to the size of the first set e to the 1 over p. That's just the LP norm of the characteristic function times the norm of f in LQ prime. And so what's often done is one defines these numbers, alpha and beta, to be, so alpha is t chi e chi f over the size of e, and beta is t chi e over, paired with chi f over the size of f. And so, for instance, this is equal to the average on f of t chi e of x. And so by duality, this is equal to chi e paired with t star chi f. And so there's a similar interpretation. So this is just the average on e of t star chi f. And so this estimate here is equivalent to showing a bound beta to the 1 over q prime, alpha to the 1 over q, less than or equal to a constant times the size of e to the 1 over p minus 1 over q. And so since p is less than q, this amounts to showing a lower bound for the volume of the set E. A little bit of motivation is, so if, for instance, if beta is big, then from a typical point, so we're looking here at chi E, and here we have an integral on f of this. So if x is a typical point in f, and if alpha is big, that means there are a lot of these guys sitting in E for a lot of points t. And so that tells us there's a lot of stuff in E, and if there's a lot of stuff in something in a set, then it's big. And beta is going to play a similar role. And so as an application of this technique, Chris established a nearly optimal theorem for this operator, the convolution with affine arc length along the moment curve. The problem was, so what he established were restricted weak type bounds. And what one wants are optimal strong type estimates. And there were some earlier methods on using for generalized Radon transforms which established strong type bounds using these characteristic function techniques. And they worked in some specific cases, but it's not, they couldn't be completely generalized. And for instance, for these one-dimensional transforms, they hadn't been used to apply strong type endpoint bounds. And so this problem in dimension 4 for this operator t, which is convolution along the moment curve, remained open in dimensions greater than 4. So recently, Chris gave another technique which involves proving a multilinear variant of this volume lower bound here, which I referred to before. And so now you will have two sets, E1 and E2, and one test set F. And so then you'll have alpha 1 and alpha 2, where you just put E1 or E2 in place here, and beta 1 and beta 2. And now you need volume lower bounds for E1 and E2 that involves some mix of beta 1 and beta 2. And also, so Chris used this to give an essentially combinatorial proof of a strong type endpoint bound for convolution with affine surface measure on the paraboloid. in d dimensions. And so this, I was able to use these techniques in order to prove an optimal LP to LQ theorem for the operator T. So we're going to let RD be the conjectured set of all P inverse Q inverse such that T from LP to LQ is a bounded operator. And it was long known that essentially for all of the points in RD, what Chris proved was that for essentially all of the points in RD, you have a bound, and I've shown the bound for all of the points. So for D greater than or equal to 2, T extends as a bounded operator from LP of RD to LQ whenever P inverse Q inverse is in RD. The main difficulties of the proof, so Chris' proof of the restricted weak type estimate was essentially combinatorial. And the main difficulty in the proof of this theorem is adapting his combinatorial arguments to show these sort of multilinear volume bounds. And it's possible that using the techniques of Tau and Wright that Gressman talked about earlier, there may be simpler proofs of such strong type estimates. There's a related thing. So there's also an improvement in Lorentz spaces that I've proved at the endpoints of R sub D. One interesting thing about this improvement, so I've clarified the situation, the endpoint for the LP to LQ estimates, but now there are sort of endpoint estimates which remain open. And so the Lorentz space estimates that I've proved are almost sharp. What is not known is whether one can replace these strict inequalities with not strict inequalities. So then finally, more recent things that are going on. So Dendrinos, Loggy, and Wright have used Chris' techniques together with a new inequality in order to establish a theorem that gives the sharp, strong type estimates for polynomial curves. So these are general polynomials, but only in low dimensions, so d equals 2 and 3. They have very well-behaved bounds. They use affine arc length, and since they're using affine arc length, they're able to obtain bounds which depend only on the degree of the polynomial and the dimension. So as far as future work goes, there's one argument that works in all dimensions, but for a very particular polynomial. And now there's an argument that works in low dimensions for all polynomials. And I think that it's possible to combine the two in order to obtain an argument for convolution. And by the way, this is still in the convolution case. I think it's possible to have a proof of the strong type endpoint bound in the convolution case for polynomial curves along the lines of this together with the argument that I used for the moment curve. And that should be forthcoming. So thank you very much.
Any questions or comments for the speaker? One of the things about the original Chris paper is that even though it is translation invariant, it's not really clear that that structure plays a really central role. Does it become more important when you add these endpoint estimates, or is it still just kind of a convenience?
I doubt. It doesn't seem any more important in that case than in the other, except that you have this very nice explicit form for a certain determinant, which is just the Vandermonde matrix, and you don't necessarily have something so nice in the Tau-Wright case.